Hi everyone, welcome to my channel. In this video, I'm going to walk you through Kafka Broker and Cluster Design for real-time event streaming. This is the foundation of the system built for scale, durability, and developer velocity. At the core of the platform are three Kafka brokers, Broker 1, Broker 2, and Broker 3. These brokers ingest, partition, replicate, and serve event data at high throughput. Each broker was deployed as a Kubernetes stateful set backed by a persistent volume claim for disk durability. These volumes store Kafka's immutable log segments and survive pod restarts or node evictions. Brokers are horizontally partitioned. For example, events like shipment.created or shipment.location.updated are spread across these brokers to ensure parallel processing and consumer scalability. Next, let's look at the ZooKeeper quorum. ZooKeeper underpins the brokers as the coordination layer. It handles leader election, cluster metadata management, and broker registration. I provisioned three ZooKeeper nodes, ZooKeeper 1, ZooKeeper 2, ZooKeeper 3 as a fault tolerant quorum. These were deployed in a separate namespace with anti-affinity rules to ensure high availability across zones. Each broker communicates with every ZooKeeper nodes for controller elections and health monitoring. ZooKeeper also ensures consistent partition state and orchestrates failover recovery when brokers go down. Next, let's look at Kafka Connect for integration. Kafka Connect acts as the bridge between Kafka and external systems. On the source side, it ingests changed data from PostgreSQL using Debezium CDC. On the sink side, it pushes data to object stores like Amazon S3 and indexing systems like Elasticsearch. Kafka Connect was deployed as a stateless deployment on Kubernetes, making it suitable for horizontal pod autoscaling. Multiple connectors can run in parallel, supporting both batch and streaming ingestion pipelines. Let's look at our next component, Schema Registry. I used Confluent compatible Schema Registry to enforce schema validation across producers and consumers. Each Avro message includes a schema ID that maps to a registered schema. Kafka Connect fetches this schema before publishing and consumers validate against it before deserialization. This enforces compatibility policies like backward or forward compatibility. The schema registry was deployed as a standalone pod inside the Kubernetes cluster. For production grade setups, consider deploying it as an HA cluster behind a load balancer or with schema replication across regions. Next, now we are going to talk about the Kubernetes orchestration. All components, Kafka Brokers, ZooKeeper, Kafka Connect, and Schema Registry were deployed inside a Kubernetes cluster. I used Helm charts for templated, reproducible deployments and enabled config maps for environment-specific configs. Kubernetes manages pod scheduling, liveness probes, scaling, and config injection. Kafka Brokers and ZooKeeper were treated as stateful services, carefully scheduled with persistent volumes and no auto-scaling. Kafka Connect and Schema Registry were stateless, deployed with auto-scaling, enabled via horizontal pod autoscalers. This orchestration strategy gave us elasticity, fault recovery, and consistent config management across staging and production. Let's walk through how the system components interact. Every broker connects to all ZooKeeper nodes for metadata sync, controller election, and partition reassignment. Kafka Connect produces and consumes messages via brokers for both inbound and outbound data flows. Before writing data, Kafka Connect validates each message using the latest Avro schema. Each broker mounts its persistent volume to store logs, ensuring durability across restarts. Kubernetes manages the entire life cycle. Deployments, failover, horizontal scaling, and rolling updates. Now let's talk about Schema Registry deployment strategy. For enterprise and multi-region scenarios, we have two Schema Registry strategies. Shared Schema Registry, all Kafka Connect instances point to a single HA Schema Registry cluster. We have simple management, but the disadvantage is that the Schema Registry becomes a single point of failure unless made highly available. The next Schema Registry strategy is to have a separate Schema Registries per region. Kafka Connect in region A connects to Schema Registry in region A, and Kafka Connect in region B connects to its local Schema Registry B. But this requires schema sync jobs between registries and must avoid schema version divergence. And also the big disadvantage here is that the Kafka Connect can't use two registries at once without custom proxy logic. The choice has to be made based on latency, governance needs, and our operational maturity. So why did I choose this setup? 3 Kafka brokers gave us strong fault tolerance and partition spread. A dedicated ZooKeeper quorum ensured consistency and fast recovery. Based on Kubernetes enabled scaling, monitoring, and centralized CI/CD, Kafka Connect standardized external data flow. Schema Registry enforced contract safety between producers and consumers. Persistent volumes preserved log history for reprocessing and debugging. Altogether, this gave us a rock-solid, observable, and flexible foundation for real-time data processing. So what I would do differently today, if I were starting over today, I would consider using a managed Kafka service like Confluent Cloud or AWS MSK to offload operational burden, adding to governance layer to track schema ownership, versions and retention, adopting tiered storage to offload older segments to S3 and keep hot partitions in Kafka. Evaluating protobuf or JSON schema where Avro imposes friction for external clients. These enhancements would further improve velocity, compliance, and scalability. So that's a wrap on building a production grade Kafka Broker and Cluster Design for real-time event streaming. Thank you for watching. I'll see you in the next video.